Test the day, everybody. So today I'm going to do a last part of this chapter. So what I'm going to do is last time when we talk about Lorentz force, we say that the current carrying conductors experience a magnetic force, and we talk about a moving charge experience a magnetic force, and then I told you last time that the electrostatics and magnetisms, electrostatics and the electricity or electrostatics and magnetisms are very correlated to each other, and these chapters somehow could relate between the electricity and the magnetisms. Alright, so now what we are going to do is, what is going to happen? Now, instead of current carrying conductor placing in a magnetic field, what I am going to put is, I am going to put a rectangular current loop in a uniform magnetic field. So we would like to see what's going to happen if we place rectangular current loop in a uniform magnetic field. So this is what we are going to see, right? and then later what we would like to see is what kind of role does this rectangular current loop play, right? So this is what we are going to see, right? So what I'm going to do is now, I consider a rectangular current loop, let's say rectangular current loops, let's say rectangle is A, B, C, D. This is the rectangular current loops. Place, right? Just place in a uniform magnetic field. Alright. B is the uniform magnetic field. Alright, so this is the direction of magnetic field is in this direction. Why? Because this is north to south. This is the direction of magnetic field. Alright. And then it's placed in a uniform magnetic fields. And this is how I place. Alright. And I have a current flowing in this direction. This is the current. Alright. This is the current flowing in this rectangular current loop. And then we say that this is the length. This is the length of loop. This is the breadth of loop. A is the length and this is the breadth and this is the length of a loop. Alright. And I supply a current and direction of current is this. Right. So what is going to happen, right? So what I'm going to do is I'm going to split this entire rectangular loop into a 4 part. Let's say like this part length BC and DA, and these two current lengths which are along a magnetic fields. This current lengths along magnetic field. All right, and then what about force, right? So we'll just come back, and force is equal to IL cross B. This is what we talk about Lorentz force. So this is equal to IL B sine theta, and we say that theta is the angle between L and B, right? Angle between L and B. So for length BC and DA, force is going to be 0, right? So force is going to be 0 for both BC and DA. It is something like this, right? I'll have this. I have a magnetic field like this. This is north pole, this is the south pole, this is A, B, C, D. Alright, so this is the direction of current, direction of length along a magnetic field. This is the direction of length, direction of magnetic field opposite to a magnetic field. So these two become a 0. Sine 0 is 0, sine 180 is 0, right? So this is what I have. Now next is I have a length AB and length CD, and these two current length are perpendicular to magnetic fields. AB and CD current lengths are perpendicular to magnetic field, right? If it is a perpendicular to magnetic fields, then I just bring this IL cross B. So force is equal to IL B sine theta. So theta is 90 degree. Now let's say the force on, let's say I just write force on AB and CDs are F is equal to I. What is the length? Length is B, so I would like to write B. Alright, sine 90 is 1. So this is the force. This is the force acting on length AB and CD. Right? This is this length AB, this length CD. So these two forces are acting on these two lengths. Now what I'm going to do is I would like to find out the direction of force. I would like to find out direction of force. Look at here. This is the length elements. This is the length. This is the direction of currents. And what is the direction of magnetic field? Yes, right. So I would like to write here L cross B. All right. This is what I have. L cross B. Right. So this is L. This is current direction is downward. So for AB, force direction is, let's say AB, force direction is downward. And what about direction in this case? This is the current goes in this direction, the length element goes in this direction, so this is what? Upward. Look at here, upward. Current direction is A, B, C, D, so this is how it goes upward. So for CD, direction is upward. Alright, so this force, the force acting on this land, this area, these two are equal and opposites, right? So the forces are equal and opposite, right? So this force and equal and opposite. So therefore, what about net force? Net force is 0, right? So net force is 0. Net force is 0. Now, however, net force is 0. However, the two forces are acting sidewise. Two forces are acting sidewise. Two forces are acting sidewise, so therefore it experiences a torque, right? Therefore it has torque. It has net torque. So how much torque? For torque means it is rotation is done about this. This is going to be axis. This is going to be axis, and this is going to be axis. This is going to be an axis. Alright, so rotation is done like this. This is done up. This rotation is done. This rotation, right? So it has a net torque. So what about the torque on a DC? Look at here. This is a torque, right? So torque number 1 is going to be, what is the torque? Again, I said torque is equal to force into perpendicular distance, right? Force into perpendicular distance. Force is equal to perpendicular distance. R cross F, right? R cross F. The directions I would like to R cross F. Alright. This is what I have force, right? So look at here. This is going to be our torque, and then the torque is going to be, this is a perpendicular distance. Perpendicular distance is A by 2. Alright, and then force is going to be, look at here, force is going to be F. Alright, So therefore, this is going to, since this is 90 degree, look at here, this is 90 degree, since this is a 90 degree, so sine 90 is going to be 1. Look at here, I just do like this. This is sine theta and a by 2 f sine 90. This is going to be a by f by 2. And what about f? F is equal to I b a divided by 2. So this is equal to I b divided by 2. Similarly, what about the second top? Similarly, second top is going to be this, right? Second top is going to be this. Alright, this is going to be like this. Alright, R equals F. Rotation is like this, right? And then, what about this? R equals F. So this is how rotation is done. This is how rotation is done, right? So therefore, this is going to be again a by 2 f sine theta, which is going to be a by 2. What about f? F is equal to I b sine 90 is 1. So therefore, finally, this is going to be I b divided by 2. So now these two tops are in the same direction. Look at here, you see these directions. You see the direction, right? You see this is rotating in a anti-clockwise. Alright, so the direction of torque is outward, right? Direction of torque is outward, right? So the total torque is going to be torque 1 plus torque 2. So therefore, this is going to be half B. What is B into A? B into A is going to be area of this rectangular current lobe, right? So this is going to be IAB. This is the top, right? This is the top. This is the top when I place a rectangular current lobes along a magnetic fields. I place a rectangular current lobe along a magnetic fields. All right. I place a rectangular current lobe along a magnetic fields. All right. This is the top when I place a rectangular current lobe along a magnetic fields. Alright. Now what I'm going to do is, now I have to do a two case. This and then with some angle, right? So when it rotates, after some time, it makes some angle with magnetic field. The plane will make some angle with magnetic field, right? So what about in case where the plane will make some angle with magnetic field, right? So this is what I have. This is what I have first. Alright. This is what I have. Now, I will do with some angle, right? Alright, so with some angle, right? That means this is the point where I have like this. I'm going to put like this. Alright, I'm going to put like this. So, I'm going to draw like this. Alright, this is A, B, C, D. And this is the normal to the, this is normal to the rectangular plane surface, and this is direction of magnetic field, and later we'll call this as a magnetic moment, right? And let's say this angle is what we call as angle theta. This is what we call as angle theta. This is what I have. So, now this is what I have, right? Now what I'm going to do is, Now a surface, the length AB, and let's say first I'm talking about length BC and DA, right? Now length BC and DA, right? DA, right? BC and DA, right? This is what I have, right? BC and DA, right? Now BC and DA, now this is not along, DA and BC's lengths are now not along B, alright? It makes some angle, right? It makes some angles, right? So therefore, not along B, but make some angles, some angle. Alright, this makes some angle, right? So why? Because now it is something like this. Alright, so this is the direction of magnetic field. This is a perpendicular. So it is making some angle, right? This is making some angle, right? So therefore, look at here. Force on BC is now not equal to 0, right? This is what I call as B sine some angle theta, right? Okay, and FB DA is equal to IB some theta, right? This is what in a way I say that AB BC is equal to DA but not equal to 0. Alright, however, now you need to see the direction, right? We have to see the directions. What about directions, right? What about directions, right? What about directions? The direction is that, look at here, this. Now the direction of magnetic field is this. Direction of a current is this, right? Direction of length element is this. This is the direction of length element, right? And this is the direction of magnetic fields. Alright. So look at here. And now look at like this. This is the direction of magnetic field, and this is direction of current elements or length elements. So now this is where is the direction of force. Force is into the plane. Force is into the planes. Force is into the plane. This is it is something like the force on this is in this direction. Force on this is going to be in this direction, right? Now let's say this is what I call as a BC. Now what about DA, right? DA direction is this. This is the magnetic field direction, right? This is the magnetic field directions. What about force, right? Look at here. This is the current elements. Look at here. This is the elements. This is the current elements. And where is the direction of force? Force is outward. This is force is outward, right? So therefore I say that directions are opposite to each other, opposite to each other, opposite to each other. This is outward, this is inward. Opposite each others, opposite to each others. However, acting along axis, acting along axis. Now look at here. These two forces are acting along axis. One goes in this direction, other goes in that direction. So they are acting along axis. If it is acting along axis, then the torque is going to be 0, right? Thus, alright, net force is 0 and net torque is also 0, right? Thus net force is 0 and net torque is also 0. So there is no, why? Because two forces are just acting along our axis, right? So they develop some kind of strains along axis, right? there is no force. The torque can be arises if and only if we have a force acting in a sidewise. So this is what I have. Now what about side? Now what about side A, B, and C3? Right? Side A, B, and side DA. Still side A, B, and DA. Still side A, B, and DA are perpendicular to each other. Still perpendicular, right? This is a magnetic field. This is a magnetic field. Still, these two are perpendicular, right? Are perpendicular to B. Thus, what about force? So force is going to be IB, B sine 90 degree. This is equal to IBB. This is a force, right? So therefore, the two forces. So therefore, forces are IBB for length AB, and forces are IBB for length. What is that? DA. Not DA, I'm sorry. This is CD, right? This is CD and this is CD. Alright. So therefore net force is what, right? Forces are equal and opposites. Forces are equal and opposites. But acting sidewise, therefore it has net torque. Therefore it has net torque. So how to find out net torque? How to find out net torques? Again, we'll discuss torque number one. What is torque? Torque is equal to force into perpendicular distance. So this is what is the perpendicular distance right here, right? What is the perpendicular distance, right? This is what I have, right? This is going to be this theta. Let's say it is theta. This is theta. This is the perpendicular distance. Let's say this is not going to be like this. This is whole thing is A. This is going to be A by 2. A by 2. This is going to be A by 2. So what is this? Alright, this is going to be sine theta, A by 2 sine theta, and how much is this? This is going to be up to this is going to be A by 2 sine theta. These are the perpendicular distance. These are the perpendicular distance. Alright, so therefore torque 1 is going to be A by 2 F sine theta, where theta, I just say theta is equal to angle between these two, right? Angle between magnetic fields and area, right? Angle between magnetic field and area, right? So therefore this is what this angle, right? Normal angle, right? Normal line, right? So therefore, what about this 2? This is again F. This is going to be A by 2 F sine theta similarly. So therefore, total torque is going to be A by 2. F is equal to IBB sine theta plus A by 2 IBB sine theta. So when I add up, finally I get IABB sine theta. This is the final answer, right? So just say I have this. So I'm going to just say I just substitute this IAB sine theta. Now I'm going to introduce a new concept. I'm going to introduce one new concept, what we call as magnetic moment, right? Magnetic moment, right? So I define a magnetic moment, right? So let's define a magnetic moment for rectangular current loop, right? Let's say current loops. So this is how I define. So magnetic moments is IA. Alright, A is the direction, or A is the area, and N. So the direction of M is along A. Now having this, and I substitute that, this is going to be MB sine theta. So this is M cross B. This is what I have, right? This is M cross B. This is what we have. So what is the theta, right? I say theta is angle between magnetic field and magnetic moment, right? And direction of magnetic moment is along the direction of area, right? So this is how to find out magnetic moment direction is very simple. If current goes in these directions, magnetic moment is downward. If current goes in these directions anti-clockwise, this is right. If current goes in the clockwise, this is down, right? This is how the direction is given by right hand rule, right? So this is, if current goes in this direction, I'm repeating, if current goes in these directions, the direction of magnetic moment is downward. Why? How to get this? If current goes in opposite directions, anti-clockwise, then direction of magnetic moment is upward. So this is how you determine a direction of magnetic moment, right? So this is what we have, right? So the torque experienced by rectangular current loop is. So therefore, what I am going to conclude here is rectangular current loop act as a magnetic dipole, right? So I just say conclusions. Rectangular current loop act as magnetic dipole moments. Magnetic dipole moments. Alright, with the magnetic dipoles, with dipole moments, this is dipole moment. This is what we have, and this is very similar to electric, right? So therefore, when I have an electric dipole put in external magnetic fields for electrostatics, P is electric dipoles. Then keeping P in electric fields, this is what we have. This is very similar, right? This is very similar, right? Now, if I have n number of turns of wires, this is for 1 turns. So, for n turns of wires, wound or rectangular current loops. So therefore, total magnetic moment would goes like this. Alright, therefore torque is going to be much greater, right? So torque is going to be this, where N is equal to NIA. Alright, where N is equal to NIA. This is what we have, right? This is what we have. So therefore, what we understood from this discussion is that the rectangular current loop acts as a magnetic dipole. Thus, when I keep this in an external magnetic field or uniform external magnetic field, it experiences a torque, right? It experiences a torque. So, a torque is going to become a zero if this is what I am going to show you now, right? If a position is like this, then torque is going to become zero. Torque is zero, right? So, I just say torque is zero for theta is equal to 0 or theta is equal to 90 degree, 180 degree. and I say a torque is going to be a maximum that is equal to MB for theta is equal to 90 degrees. So that's you should keep in mind. So you will be having throughout the rotations, the torque varies from 0 to maximums. Torque varies from 0 to maximums. All right. Now next what I'm going to discuss is a circular current loop as a magnetic dipole. Circular current loop as a magnetic dipole. So we say the rectangular current loop is a magnetic dipole, and obviously we say that circular current loop must be magnetic dipole. So right. So I'm going to borrow an equation that we have done last time, that is magnetic field along the axis of a circular current loop. Right. Magnetic field along the axis of circular current loop. Axis. I just read it. Axis of circular current loops. So therefore, this is how. This is the equation that we obtained. Alright, this is the equation, right? This is the equations. So I'll be having, this is circular magnetic. I take this is distance is x. Alright, and the direction of magnetic field is this. Alright, so what is the magnetic field at this point, right? Magnetic field at this point is given by this. This is what we have done, right? So that magnetic field is only along axis. So now what we would like to do is, let's say at the center, right? Say first, so what I'm going to do is, R is x, that is the distance from center, is very big compared to R. R is a radius of circular current loop. R is a radius of circular current loop. I is a current. Mu is magnetic permeability. Alright. So this is, if this case, then axis would be equal to mu naught I R squared divided by 2 or x cube. This is what we get. And now what I'm going to do is, I will just put pi divided and multiplied by pi. If I divide and multiply by pi R squared is area, right? So this is what I have. This is area divided by 2 pi x cube. Okay, what is area? What is IA? Alright, we say that IA is equal to magnetic moment is equal to IA. Alright, so therefore magnetic field along axis would be equal to mu naught m divided by 2 pi x cube, and divide and multiply by 2, 4 pi x cubes, and showing your directions, so you would get 4 pi 2m divided by x cube. This is the answer, right? So this is the magnetic field along axis. This is the magnetic field along axis. This is the magnetic field along axis. Alright. And this is very similar to electric field. When I have an electric dipole, what about electric field at a point on an axis of dipole is very similar. Electric field at axis is going to be 1 by 4 pi epsilon naught 2p divided by r cube. This is what we have. Very similar, right? Similarly, I can go and find out equatorial planes. So therefore, equatorial plane would be equal to mu naught divided by 4 pi m divided by x cubes. This is for magnetisms, and for electrostatics, what we have is this. This is P. Instead of P, I have instead of M, we'll have P. Right? This is what we have. And again, I say therefore M corresponding to P. M is for magnetisms and P is for electrostatics. M is for magnetisms. So therefore we say the circular current loop act as a magnetic dipole. Circular current loop act as a magnetic dipoles. So therefore, circular current loop acts as a magnetic dipole. So this is what we have in case of circular current loop. So this tells you that circular current loop acts as a magnetic dipole. So now we would like to see now revolving electrons. Let me recapitulate. Maybe in class 11 you studied this in chemistry, right? So Bohr model of hydrogen atom. So when we talk about Bohr model of atoms, we say that electrons are revolving around the nucleus. So I say this is going to be a nucleus having Ze charge, and electron goes around the nucleus like this. And this is the radius, this is the radius, this is the radius. This is the Bohr model of hydrogen atom. So this is electron. It is very similar to arc going around sun, right? In case of arc going around suns, it's all because of gravitational force. However, in case of electron going around nucleus, it is electrostatic force between a nucleus and electrons. Electron is carrying a negative charge. Electron is carrying a negative charge, and then the center will have a positive charge. So there will be attractions due to which electron goes around a nucleus. Electron goes around. Now what we are going to prove you is this revolving electron act as a magnetic dipole. So revolving electron act as a magnetic dipole. So we would like to find out this and try to understand the structure of atoms. And we know that the Bohr model somehow could explains the hydrogen atoms, and how what about the magnetic moment in case of hydrogen atoms. So every atom should possess a magnetic moment if we go according to this theory, right? So this is what I have, right? So the magnetic dipole moment of a revolving electron. So what I have is, so electrons going around the nucleus, alright. So T is the time period. T is the time period. So current is going to be is going to be a charge divided by, alright, charge divided by this is what we call the rate of flow of charge. So rate of flow of charge means velocity divided by time period, right? This is what we call as a rate of flow of charge, right? So therefore this is what I have, right? What about time period? What about time period? So time period is going to be 2 pi r divided by velocity, right? I'm sorry, this is going to be a Q, right? This is rate of flow of charge, right? This is the rate of flow of charge. Now I say, now since actually electrons are going around, since we are taking a current, it is a positive charge that is going around nucleus, right? So if electron goes in these directions, the positive charge should go in that directions, all right? So I would like to show this is the positive charge. This is the positive charge going in that direction, right? Why? Because it is just the opposite, right? Nothing wrong, right? So therefore, what about current then? So therefore, current would be equal to, I substitute this. So E V divided by 2 pi R. R is a radius. R is a radius. All right. Now what I'm going to do is, what about magnetic moment, right? So magnetic moment is equal to IA. All right. What is IA? I is the current. A is pi R square, right? So therefore, I is equal to E V divided by 2 pi R, then pi R square, cancel out. Finally, we get this is equal to E V R divided by 2. This is a magnetic moment. This is the magnetic moment. This is the magnetic moment of revolving electron. This is the magnetic moment of revolving electrons, right? Alright, this is M is the magnetic moment of revolving electron. So now what I'm going to do is this M, alright, E, I just divide and multiply by ME. I just divide and multiply by ME, alright. So if I divide and multiply by ME, what I'm going to get is, this is what I have. MVR. MVR is what we define as angular momentums. MVR is what we define as angular momentums. So I just say N is angular momentum, right? N is angular momentums. Angular momentum is this is defined in class 11, right? This is angular momentums. This is angular momentums. So therefore, magnetic moment would be E L divided by 2ME. So the direction is going to be this, right? So direction is this is the direction. Direction of angular momentums is along a direction of direction of magnetic moment is along a direction of angular momentum. So this is what we have. Now what I'm going to define is one more term. I'm going to define is what we call as gyromagnetic moment, right? So I just divide. This is a constant. This is a constant, and this ratio is what we term as a gyromagnetic moment. This constant is what we call as gyromagnetic moment, right? This constant is what we term as a gyromagnetic moments. The value of this gyromagnetic moment is equal to 8.8 into 10 raised to power minus 10 raised to power 10 coulomb per kg. And look at here, these gyromagnetic moments, the experimental value and the theoretical value of gyromagnetic moments, right, match each other. So the Bohr magnetic moment, Bohr concept of revolving electrons or the magnetic moment is somehow fixed experimentally, right? So this is very essential. Whenever we do physics, alright, whatever you propose should go according with experiment, right? So this is what exactly it has gone, right? So this is what we call as a gyromagnetic moments, right? So again, I would like to bring one more concept, that is Bohr. Bohr says that electron doesn't take arbitrary orbits. Electron takes only specific orbit, and that is what we call as and what about that orbit? He said that angular momentums is always equal to integral multiple of s by 2 pi. This is the Bohr postulates. So Bohr says that electron always takes a particular angular momentums or orbits having angular momentum. This is what we talk about angular momentum, right? So therefore, magnetic moment is equal to, alright, E L divided by 2ME, and then instead of M, I'm going to add instead of L, I'm going to add HLE 2 pi. So M is equal to N HE divided by 4 pi ME. This is where N is what we call as principal quantum number, right? For first orbit, N is equal to 1. So therefore, magnetic moment would be equal to HE divided by 4 pi. And this is the smallest angular momentum, right? This is the smallest magnetic moment, right? And the value of this smallest magnetic moment is equal to 9.2. This is for hydrogen atoms. Ampere meter square. And this is what we call as Bohr magnetron. This is what we call as Bohr magnetrons. This is what we call as a Bohr, the smallest magnetic moment of an hydrogen atom. So if I go higher n, the number is going to increase, right? So So what we understood from this concept, this lesson, is that revolving electron act as a magnetic moment. So therefore, atom has magnetic moments. So the very origin of magnetic moments, the magnetic properties, are again because of the subatomic particle, that is the electron going around nucleus. Electron going around nucleus behave like a magnetic moment, behave like a magnets, and this is how atoms act as magnetic. Atom has a magnet. The property of the magnetic property of atom is originated from the revolving electron around the nucleus. Right. So thank you. Next class, I would like to do galvanometer. Thank you.